Getting started in Chapter 9. Chapter 9 is our study of thermodynamics, where we put together energy and chemistry. Now, the first section or insight we are going to skip, but it is a nice little introduction to energy use and the world economy. And I think it frames this chapter nicely if you want or have time to give that a read. We are going to jump into section 1, however, and talk about defining energy. There's two broad categories that energy is categorized in or as, and that's potential versus kinetic. Right? Potential energy is associated with the position of an object, whereas the kinetic energy is associated with motion. This is usually the definitions that you get early on in middle school and high school science classes. If you think about holding a pen or some object, we will say object here, and you take that object, what am I doing? Let's see. Here we go. You take that object and you raise it over your head, right? That object now has more potential energy. If you drop it, right, that energy is turned into kinetic energy. That energy is released as it is in motion. Now, energy is categorized in other ways as well. For instance, chemical energy, right? This is what we're going to be interested in as we're in a chemistry class. And that's going to be energy released or absorbed during a chemical reaction. Energy that is released when bonds break or energy that is released or absorbed when bonds break and bonds form. We are going to be interested in the internal energy, right? That's going to be that combined kinetic and potential energies of a system. In this case, again, chemistry related, we're looking at atoms and molecules in a reaction that we're studying. There's other forms of energy: radiant, mechanical, thermal, electrical, and nuclear. And these are important, but in this class, we are going to be more focused on chemical energy. We'll certainly touch on thermal. You'll see some relationships between mechanical and electrical. But of course, again, that focus is going to be on chemical energy and the internal energy of chemical systems. Thermochemistry is just putting this all together, right? We are studying the energetic consequences of chemistry, the release and absorption of energy when we get to chemical reactions. Now, energy can't be created or destroyed, but it can be transferred, right? And there's only two ways that energy can be transferred, and that is heat and work. Heat, which will be denoted with a Q, and work with a W, are two ways that we can move energy from one object to another, right? Heat is the flow of energy because of temperature difference, right? So when we think about, let's say we have two objects, one is hot, one is cold. All that means is one has a higher temperature than the other. Energy will always flow from hot to cold. Cold is not like a substance. If you say something is making you cold, what's happening is it is at a lower temperature than you. Say you're holding an ice cube. That ice cube's at a lower temperature than you are. And heat from your body is leaving you and going into the ice, right? The cold is not coming into you. It's always a flow from hot to cold. All right, so from hot to cold. It's an important note. We can also transfer energy with work, right? This is going to be accomplished by a force moving a mass some distance, right? So when we thought about pushing that object up into the air, say like I push my pen and I hold it up over my head, right? I have transferred energy into that pen, right, by moving it a distance against a resistance. In this case, that resistance is gravity. Now, we aren't going to be picking atoms up and moving them up and down. we're going to be interested in something called pressure. Oh, nope. Let's go back to my highlighter. Pressure volume work. So the movement is going to be expansion or compression of a gas and against an external pressure. This is going to be the most common work type in chemistry. There are other types of work as well. We're going to concentrate on PV work. Now we're going to be doing calculations, right? And if we're doing calculations, we're taking measurements, we are quantifying energy changes, we're going to need to talk about units. The SI unit, and the one that you're going to most frequently deal with here, is the joule, right? It is a derived unit, meaning that it is derived from our 7 base units, right? And it is a kilogram meter squared per second squared. You don't need to memorize this, but it is good to recognize during some calculations. If you're dealing with masses, they're going to have to be in kilograms, right? Accelerations, meters squared per second squared, or I'm sorry, meters per second squared. And then distance, right, is in meters. So we may, as always, have to keep track of our units. There are other common energy units like the British thermal unit and the calorie. The calorie is one that is likely very recognizable to you, right, in terms of nutrition at least. But a calorie is defined as how much energy is used to heat 1 gram of water by 1 degree. That amount of energy is 4.184 joules, right? And so that is the relationship between calorie and joules. Now, something that people often misunderstand is the calorie on the nutrition label of your food item or your drink is not this lowercase c calorie. It's big C calorie. And big C calorie here is really a kilocalorie. All right, so 1 big C calorie equals 1,000 little c calories. This is important if you're using thermochemistry and thermodynamics to study the energy content of food. If you don't know that nutritional calories are really kilocalories, right, you may come up with, oh, you have this snack that's, 200 nutritional calories, but you've calculated it with lowercase c calories, right? You're going to be off by 1,000. Nobody is going to want to eat that snack, right? So it's important to keep track of these units. Moving on to section 3 here, we're going to talk about the first law of thermodynamics. Now, I've included this in your notes, I think, before it comes up in the slides. Although it does say it here, right? The total energy must be conserved. The first law of thermodynamics is an important, obviously it's an important thing. It's the first law of thermodynamics. It's something that you should know. We've said it already, but here it is spelled out. Energy can be transformed from one type to another, maybe from chemical energy to thermal energy, mechanical to, usually it's to thermal, but it cannot be created or destroyed. The universe doesn't lose or gain heat. The total energy of the universe is constant. So that is the first law of thermodynamics. That's going to drive a lot of our calculations here, and it's just something that you should know. Now, we're going to talk a lot about our system that we are studying, right? The system is just the part of the universe that you are studying. Now, that's pretty broad, right? If we're looking at a chemical reaction, then the system is the chemical reaction inside the container, right? But when you look at thermodynamic studies, that it can be, your system could be the whole planet. The system could be a car engine, right? It depends on what you're studying. The surrounding is literally everything else in the universe. Now, we often don't study the entire universe. We we'll look at immediate surroundings. But in general, the definitions, systems plus surroundings should equal the universe, right? So if your system loses energy, the surroundings should gain that much energy. The system and surroundings are separated by some sort of boundary. In our case, it's often a flask or a balloon. Sometimes it's the piston of an engine. If we're looking at the Earth versus the solar system, right, then the system and the surroundings might be separated by the atmospheric layer, right? It depends on what you're studying, but it's important that the boundary is defined. Now, let's look at these little equations that are popping up. Delta E is the change in energy of your system or of your surroundings. But the change in energy, whatever it is that you're looking for, has to be equal to the heat flow and the work, right? Heat flowing in or out, work being done on or by. These are the only two ways that we can transfer energy. So this is the only way that we can get a change, or delta E, change in energy. Delta, you're going to see a lot in this chapter. This little delta symbol means change. It's always final minus initial, right? This is important. We're going to see this over and over again when we get to enthalpy and entropy. Gives free energy. You're going to see this delta sign. It's always final minus initial. Sign is going to be very important, right? Positive and negative signs. So before we do that problem, let's talk about that. All right, a plus sign in front of W. Let's expand this a little bit. Red is aggressive. Let's get back to our blue. A positive amount of work is work done on the system, right? We are putting energy into the system by doing work on the system. Negative W is work done by the system, right? If you have a system that is expanding and pushing against the external pressure, then it is going to lose energy. That energy is being transferred to the surroundings. A positive heat flow is going to be, let's see, how do we say this? Heat entering the system, right? So if you are heating a reaction, that's going to be a plus Q. The delta E of the system will be going up because you are adding thermal energy. A negative Q means heat is being lost by the system. All right. Oftentimes, a plus or a minus is not shown, but it is given through words in a problem. So it is important that you understand how to read the words. All right. So we're going to look at a very simple delta E problem. If we have 15 joules of heat added to a gas, and that gas does 218 joules worth of work, what is the delta E of the system? All right, so our Q, right, 15 joules of heat are added to the gas. So that's going to be a positive, let's try that again. That is going to be a positive 515 joules. Now, the gas does work as a result. So the gas is doing work, the system is doing work. That's going to be a negative 218 joules. So what's the overall change in energy of the system? Well, delta E equals Q plus W. So it equals a positive 515 joules plus a negative 218 joules. All right, so 515... Oh, sorry, pardon me. 515 minus 218 is 297 joules. And that is a positive number, which is important, right? 297 joules. That means the overall energy of the system increased 297 joules. You should practice problems like this. They're deceptively easy. The math is obviously very easy. You're adding or subtracting. But if you don't carefully read the problem and you get a sign wrong, it's very easy to mess this type of problem up. And these should be some easy points. We will... Okay, there we go. Always making sure that we remember that first law of thermodynamics. We will jump into part 2.